quick note before we proceed, this last comment that in the Hasse diagram of a parse-ordered set, two elements are in the same connected component except when they are comparable. Unfortunately, I was wrong about that. It's not true at all. Oops. But okay, let's continue on to talking about connectedness in directed graphs. So basically, you make exactly the same definition, but the behavior, the flavor, is quite different. So we have some new names for it, and we'll look at some more examples. So a directed graph is strongly connected if basically the same definition you gave before. If there's a path from any vertex to any other. In particular, unlike the case of undirected graphs, this time we have to worry about directions. So in particular, we're saying in both directions between any two pair of vertices. So from A to B, and from B to A. And if we're going to call this strongly connected, then what is the alternative? So let's take a quick, another little definition. Every directed graph has an underlying undirected graph which you find by just forgetting the edge directions. So if we have a graph like this, which is a directed graph, then if we just draw the same graph with no directions on the edges, then this is what we call the underlying undirected graph. And basically, this is important to consider also when we're working with directed graphs. And this is what forms our definition of weakly connected. So a directed graph is weakly connected if its underlying undirected graph is connected. So, well, before we do some examples, let's note it. Let's make our definitions of components as well. Again, it's basically the same, but let's write it down. A maximal strongly / weakly connected component, connected subgraph, is a connected component of that name. Connected subgraph is called a strong / weak component. Right. So the difference with directed graphs, the point of making these definitions, is that strong and weak connectivity behave very differently. Whereas for an undirected graph, you can immediately look at it and very easily see whether it is connected or not, for a directed graph, it can be much more subtle. So here are two different triangles. This one on the left is strongly connected because, for example, you can get from this vertex to this vertex, not through this path because that's going backwards, but through this path along those two edges. And for example, you can get from this vertex to this vertex and this vertex by taking that path or that path, and so on and so forth. Basically, since these edges are going in a circle, you can get from anywhere to anywhere else. This graph, on the other hand, is weakly connected. It is not strongly connected. Because, for example, you can get from this vertex to this vertex by going along that edge, but there is no way to go back the other direction because this edge is in the wrong direction, and this edge is also in the wrong direction. So neither of these vertices can reach back to the bottom left guy. So there is not a path. Let me write that down. It is not strongly connected. For example, call this A and this B. There is no path from A to B. So with directed graphs, it's basically the same problem and basically as easy to pick out weakly connected components, but strongly connected components can be much harder to just look at a graph and see immediately. So let's have an example. And let me copy it carefully from my notes because it is hard to see and correspondingly easy to mess up. So I think these directions. Okay, so here is a directed graph. Let us try to analyze what are the strong components. So first of all, it is weakly connected. It is not strongly connected. So for example, because these two middle edges are both going to the right, we'll never be able to get back from that side to this side. So that is telling us that this and this are going to be, they are not strongly connected because you can only go one direction. So for example, if this is A and this is B, there is no path from A to B. So let's dig a little deeper. We know that these two sides are not in the same strong component. So let's look at those sides individually. On this side, our edges are going in a circle. So this is the case over here. This is strongly connected. Since it's going in a cycle, we can get to any point from any other point. So the strong components, let's start drawing this picture. Let me start with just drawing all the vertices. And then we'll add edges to show which ones are in the same component. So these three we have concluded are in the same strong component. And what about these other three? Well, these edges are going not in a cycle. There are two edges coming into this vertex and two edges coming out of this vertex. So let's check carefully what are the strong components of this graph, namely, what are the maximal strongly connected subgraphs? Well, from this point, we can get to either of these points, but we cannot get back from either one of them. So neither that nor that is strongly connected, so this point has got to be on its own as a strong component. And similarly, this point we can get here, but we cannot get back. So this is not a strong component either, and these points must also be on their own. So the strong components, we have finished drawing the picture. There are 4 of them. As we have drawn here, this triangle is a strongly connected component, and each of these vertices by itself is a strong component. So you can see that the detecting strong components rather than weak components is much harder to see from the graph alone. It depends very much on the directions of the edges.